What's up, everybody? Welcome to lecture 7.2 of trig. Today we're going to be talking about the inverse functions for trig functions. To start off with, I thought we'd look at sine. So, for the function sine of x, we know the domain is negative infinity to infinity, and the range is negative 1 to 1. Now, some of you might be looking at that like, hold on, wait, what is domain, what is range? Well, domain is the set of all possible inputs that has an output. So let's say you put an x value in and it gave you an output. It's in your domain. Now let's say you chose another x value and it didn't have an answer. Then it's not part of your domain. Range is kind of the same idea, except it's all of your outputs. It's just the set of all possible outputs. And notice the notation that I use here. What I'm saying is the domain is the interval from negative infinity to infinity. This means it's all the possible x values from negative infinity to infinity. The range, I'm saying, is negative 1 to 1. So it's all the y values from negative 1 up to and including 1. Also notice the notation is a bit different here. One uses a rounded bracket, a rounded brace. The other one uses a square brace. There's a reason for that. A rounded brace means you can't include that value. You can go all the way up to, but you can't include it. The square brackets mean you can include that value. So we'll never reach infinity, so we use rounded brackets. We can reach 1, so we use square brackets. In fact, I shouldn't say it, we can reach 1, we do reach 1, so we use square brackets. Okay, well, like I said, we want to find the inverse function for sine. But in our last lecture, I told y'all a function has to be injective in order for it to have an inverse. And this is not injective, is it? Not even by a long shot. Like, we go from negative 1 here, we're already back at negative 1. We've only gone 2 pi away from where we started, and we're back at negative 1. We have a 1 here, go 2 pi away, and we're back at 1. We go negative 2 pi away, I should have said. And that's true for every point in here, right? Like, we keep repeating all of these points from y equal to negative 1 up to y equal to 1. So it's not injective. It fails that horizontal line test over and over and over again. Okay, so how are we going to address that? Well, I also told you in the last class, we can restrict our domain. Okay, what does that look like? What does that mean? We can restrict our domain. Well, it just means we can say, all right, I just want to look at a small window, a sliver of the entire domain. But we have to choose it really carefully here. We have to choose it so that our function is injective on the restricted domain. Okay, so I'm throwing a lot of jargon at y'all. What does all of this mean? What does it look like? What it means, what it looks like, is something like this. So we've got our function here. Like, okay, I want to pick a bunch of x values such that my function is going to be injective inside of those x values, inside of that interval. So looking at it, it seems logical to start with one of our maximums or minimums, right? So one of the high peaks or the low valleys. So let's start there. Let's start here at pi equal, or at x equal to negative 2. X equal to negative pi over 2. I apologize, I can't talk today. It's like 1 in the morning right now. So, we're starting at the point where x is equal to negative pi over 2. We're going to move to the right. We're going to keep moving, we're going to keep moving. We're going to get to the place where x is equal to pi over 2. We're going to notice if I move a little bit more to the right, I get a y output that I've already had. Well, that's problematic because that means it fails to be injective then. So I guess we just have to restrict ourselves to x equal to negative pi over 2 up to x equal to pi over 2. We have to use this chunk of our x values. Negative pi over 2 is less than or equal to x is less than or equal to pi over 2. You can also write that in interval notation using the square brackets. Okay. Well, before we do anything else, let's look at this a little bit more closely graphically. Let's imagine we put a box around these sets of points. Okay, let's graph that over here. Graphing that over here, it's going to look something like this, right? So this is going to be sine of x equal to y when we restrict the domain so that x is between negative pi over 2 and pi over 2. So this is still sine of x equal to y, just restricted. And looking at it this way, we can definitely see it's injective. Okay. Well, we haven't talked yet about the inverse function of sine, but before we do, I want to ask, what does the graph of this look like? If we were to graph the inverse function of this, I said last class, the graph of an inverse function is just the reflection of the graph of the function across the line x equal to y. So, having said that, we can guess at what the graph of this is going to look, the graph of the inverse function is going to look like. We know that this is the point 1 pi over 2. This is the point negative 1. My mistake, I wrote those backwards. Like I said, it is midnight. Or 1 o'clock, I mean. And this is negative pi over 2 and 1. Negative 1. Alright. Well, the graph of the inverse of this is just the reflection across that line x equal to y. This is going to be pretty easy to draw then, isn't it? Just going to flip the x and the y values. That's it. Alright, so let's do that. Let's graph this. All right, so the graph of the inverse function of sine, we know is going to look something like this, right? Like I said, it's just flipped across that line x equal to y. Okay, so what do we call this then? We need a name for it, right? We could call it two different things, sine inverse, or we also call it arc sine. This has two different names. Arc sine of x, or sine inverse of x. Okay. So this is the graph of what's called arc sine of x, or equivalently, we can also call it sine inverse of x. Huh. Why do you think it might be called arc sine of x? Why that? What's going on there? Well, what's happening is if we have a unit circle, and we know the y value along at one point along the edge, the arc sine will give us the arc length between that point 1, 0 up to whatever the other point is. And I'll show this in a little bit here. If I forget to show it in this lecture, remind me and I'll show it in another one. Okay, so let's talk a little bit about this arc sine. All right, so I'm about to lay some truth bombs on y'all. A bunch of them, actually. Start off with, like we've already said, the graph of arc sine looks about like this, right? It has a domain from -1 to 1, -1 to 1, and a range of -π/2 to π/2. Now notice, when we were talking about that restricted sign, the domain and range were these but flipped, right? And we should expect that, because what we're trying to do, we're trying to say, all right, if x gets us to y, what's the function that takes us from y back to x? So we should expect the domain and range of the two functions to flip. Like I said, this is the domain and range of the restricted sign. Having said that, you got this other fact here too, that the arc sine of x is equal to y if and only if sine of y is equal to x. Okay, that makes sense. We're going one way. We're going from arc sine to x, and then we're going back from y back to x. Okay, they're inverse functions of each other. We should expect that. And then finally, if x is between -1 and 1, then the sine of arc sine of x is equal to x. And if y is between -π/2 and π/2, then the arc sine of the sine of y is going to be equal to y. Now let's think about this. What are we doing? What are we saying? Well, it comes back to this middle definition here. Here we're saying we want to take the sine of arc sine, right? Well, we know arc sine takes in an x value, spits out a y value. And we know sine takes in a y value, spits out an x value. So if we take arc sine and put it inside of here, arc sine is really y, and sine of y is really x. So since we're taking the combination of the two, we just get back to where we started. And the exact opposite direction happens here. Okay, how are we going to use it? What are we going to do with this? Why, like, this is abstract and weird. All right, fair enough. Let's look at two different examples then. So to tackle these first two examples, we're going to use these three properties, these three facts. To start off with, I want you all to notice, this first example, we're trying to find out what theta is, right? Well, we know in this setup that sine of theta is equal to the square root of 2 over 2. And what we're asking is that we solve the arc sine of the square root of 2 over 2 equal to theta. Notice also something I've kind of just brushed over thus far. These angles, because of our restriction, that they have to be from negative pi over 2 to pi over 2, these angles can only come from the right side of our unit circle. So let's use that to kind of guide our thinking, right? If that's the case, we're looking at the point square root of 2 over 2. That's going to be somewhere up here, right? Well, that means on the right side, we have to just pick this one, right? You only pick the top right corner. The only time that can happen is if theta is equal to pi over 4. So it must be the case that arc sine of the square root of 2 over 2 is equal to pi over 4. Now there's another way to think about this. There are only two possible angles that we can put into sine and get out the square root of 2 over 2. One of those angles is pi over 4. The other angle is 3 pi over 4. But 3 pi over 4 is larger than pi over 2, so we can't use it. We have to use the other one. That's one way to think about it. The other way to think about it, like I said, is using this geometric approach. What we're looking for is the square root of 2 over 2. We have to use the right side of the triangle, or of the unit circle. And the only angle on the right side of the unit circle that has a sine of the square root of 2 over 2 is pi over 4. Okay. So this is one way of using this arc sine. This other example, we want to find the angle such that sine is going to be equal to 1/2. How do we know that? Well, we can recall on the unit circle, our xy coordinates are equal to our trig functions, right? So what I mean is, on our unit circle, if we recall, the xy position of any one point along the edge of our unit circle is equal to the cosine of that angle and the sine of that angle. Cool. Because of this, I'll write this slightly different. Because of this, we know that sine theta is equal to 1/2. And we know that the arc sine of theta is equal to theta. Okay. So what this is saying is the arc sine of 1/2 is equal to our angle, right? That's all we're really saying. But because of this, we can look over here and we can say, all right, cool. I know that the theta, the angle, has to be pi over 6, right? It has to be pi over 6 because if we look, sorry, I just froze for a second there. If we look at what happens, pi over 6 is the only angle that's going to give us a value of sine equal to 1/2. So it must be the case that this is equal to pi over 6. Now what I was thinking about when I froze there for just a second was how I wanted to talk about this next part. Earlier in the video, I said I was going to explain why this is called the arc sine. So let's look at this. The reason why this is called the arc sine has everything to do with the arc length. So we know that the arc length right here, let me actually write this in green. Arc length, S, is equal to r times theta, right? But our trig functions are defined on the unit circle. So r, we automatically know it's just going to be 1. So on the unit circle, the arc length is just equal to the angle. So every time we find the angle, we're finding the arc length on our unit circle. So what I mean to say is, in this particular problem, what we've done is we've said we want to find the y value, the angle, such that we're restricting it to just this half of the circle, and we know the sine of that angle is going to be 1/2. That gives us a point on the edge of the circle. It gives us the point, the square root of 3 over 2, and 1/2. Okay. Well, if I wanted to find the arc length from theta equal to 0 up to that point, that's going to be equal to that's going to be equal to r times theta. But we know it's a unit circle, so r is equal to 1. So the arc length is equal to theta. So this arc length is equal to just the angle. So every time we find the angle using our inverse sine, we're finding the arc length of this segment here. And that's why it's called arc sine, because it's quite literally finding the length of the arc. Cool. Let's move on. Now before we move on to cosine, I really quickly wanted to touch on one last example, something that I think might help clarify all of this a little bit more, especially since we don't get to have that sit down and talk face to face in class, right? So you don't get to ask me the questions that you might have in the usual way. So as a way of addressing those questions in advance, I hope, thought we'd try one more example. So in this last example, we want to find out what the arc sign is of negative 1/2. So we want to find the arc sign of negative 1/2. Well, whatever the arc sign of negative 1/2 is, we know the sine of that angle is going to be equal to negative 1/2. Okay. Well, if we take this back to a unit circle type perspective, what this tells us is whatever the angle is, the y value of our point at that angle is negative 1/2. So we can take it back to the unit circle and think of it there. This is the line y equal to negative 1/2. So there are only two possible angles on our unit circle that gives us a sine of negative 1/2. Those and those, right? These two. Well, depending upon how we measure these, they both have an angle larger than pi over 2 or smaller than, my mistake, I shouldn't say smaller than. They both have an angle larger than pi over 2. If we measure them this way, right? But we don't have to. We could measure them moving in the opposite direction. Once I get this all erased. Okay. Now notice, moving in this direction, pi over 2, negative pi over 2 I should say, happens here. It happens at the y-axis. So we know we can't include this point, right? We shouldn't even think about it. We should only be looking at angles that answer our question on the right half of the circle. So, erase all of this. The only way we can possibly get y is equal to negative 1/2 on the right side of the circle is with this angle right here. So looking at our unit circle, we say, all right, well, I know what that is. This is the angle. Theta is equal to negative pi over 6. So the arc sine of negative 1/2 must be negative pi over 6. Now the way we did this was by saying, all right, we're restricting ourselves only to angles from negative pi over 2 up to pi over 2. So that means we're just restricting ourselves to the right side of the circle. And when we do that, we find the only possible point that fits this description is this one right here. And it only occurs at an angle of negative pi over 6. So this is the geometric interpretation of the arc sine. Well, one of the geometric interpretations. And now, like I've said before, in that previous example, something else that's really particularly cool, I think anyhow, about this arc sine is that it's not just equal to the angle on the unit circle, it's equal to the arc length traced by that angle. So, having said that, let's move on. All right, so to find the arc cosine, before we start really talking about it, let's make a couple observations about cosine. Start off with, the domain of cosine is going to be all real numbers, right? So from negative infinity up to infinity. And the range of cosine is going to be from negative 1 up to 1, and including both of those values. All right. Well, looking at this, we can see it's not injective. It keeps failing the horizontal line test over and over and over again. So how are we going to handle that? Well, we know we're going to need to restrict it, right? Like, we need to restrict the domain. So what are we going to use? Well, looking at the graph, an obvious choice jumps out at us. If we restrict our domain to be from 0 to pi, x equal to 0, x equal to pi, we end up with just this chunk. And this chunk is definitely injective. So just so we can see that, let's graph it over here. It's going to look something like this. And we said that this is the graph of cosine of x equal to y, restricting x to be the interval from 0 to pi inclusive. So we're including 0 and pi, and we're saying x can be any number between them. All right. Well, we should probably make some observations here. First off, this point is the point 0, 1, and this point is the point pi, negative 1. We could probably make one more observation. This point right here is the point pi over 2, 0. Okay. So now we want to find the graph of arc cosine. Well, we know it's the mirror image of this graph across the line x equal to y. So we're just going to flip it, right? If we do that, then the graph of arc cosine is going to be this graph. Where this is the point negative 1 pi. this is the point 0 pi over 2. And this is the point, this bottom point here, this is the point 1, comma, 0. It's 1, comma, 0 over here. All right, so we know what the graph looks like. What's the domain? Well, the domain's just going to be from -1 to 1, right? Because we're taking in, using a different color again, we're taking in every value from x equal to -1 up to x equal to 1. So our domain must be from -1 to 1. Now our range, well, our range is from 0 to pi, because that's all the y outputs it gives us, right? So the range is 0 to pi. And because we're including these values, remember we use square brackets whenever we go up to that point and we include that point. All right. Well, let's think about this for a second. Cosine takes in an angle and it computes a value, right? And what we just said is that we're going to restrict our angles to 0 to pi. So where are we looking on the unit circle? What area does that correspond to? Well, we can draw it. If we want to restrict ourselves to just the angles from 0 to pi, then that would be this top half. So whenever we want to use the unit circle to help us solve things for arc cosine, we need to use the upper half of the circle. Okay. So we've talked about cosine, we've talked about sine. What about tangent? What does tangent look like? Let's look at it. So before we go any further and look at the arc tangent, let's look at tangent, because things get a little bit hairy here. And they get hairy here because of what we called asymptotes, right? These asymptotes were x values that we could get as close as we like to, but we can never put that into our tangent. So we will never be able to put in -pi/2 into tangent and get an answer. And because of that, we have a vertical asymptote at -pi/2. So we can take x values and make them smaller, 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 and approach -pi/2, but we'll never be able to put in -pi/2. Because it just doesn't have an answer. It doesn't compute anything for us. And the same is true for x equal to pi/2. We'll never be able to put x equal to pi/2 into our tangent. So because of that, we have another vertical asymptote. And these repeated every pi intervals. So they kept repeating pi intervals. So because of that, our domain gets a little, let's say, cattywampus. Gets a little cattywampus on us. And it gets funny like this because what ends up happening is in our domain, we can't include negative pi over 2. And we can't include pi over 2. And every value pi away from those, we can't include. So we have to do something to account for that. And to account for it, we say that the domain of tangent of x equal to y is negative pi over 2 plus n pi to pi over 2 plus n pi, not including either of those values, where n is an integer. So what does this mean? Well, this means you can take any integer, negative 1, negative 2, negative 3, 4, 5, 12, 2,000, whatever you want. Just has to be an integer number. You can take that and put it in for either n. So you have to take the same value and put it into both ends. And that's going to be the domain for part, and that's going to be the boundary for a particular chunk of our tangent. So what we're really doing is saying, all right, it is continuous in this domain, and it's periodic, repeating over and over and over in both directions. So if we take an interval that is pi times some integer number, and look that far away, we'll see our graph repeat itself. That's all this is really saying. Beyond that, the range is pretty obvious, right? We're literally going from negative infinity. We can go as far down as we want. We can go as far up as we want. Now, as hairy as this is, because we're literally saying you can go up to negative pi over 2 and up to pi over 2, but you can't include those values. That's hairy, I know, and it's going to take some time to get used to this idea. But because of it, we have a really nice way of restricting our tangent. We can say, I don't care about everything else on either side. I just care about this chunk. Because I just care about this chunk, we can go ahead and flip it across that line x equal to y, and I can find the graph of arc tangent. So what does that look like? Let's look at it. All right, so we're just taking that mirror image, like I said, right? Taking the mirror image across the line x equal to y. And when we do that, our arc tangent is going to look a bit like this graph. So breaking it down, what we've got is our asymptotes are no longer at x equal to negative pi over 2 and x equal to pi over 2. Now they're at y is equal to pi over 2 and y is equal to negative pi over 2. The domain, so all the x values that we can put into arctangent, the domain of arctangent is from negative infinity to infinity, and the range is from negative pi over 2 to negative pi over, or the range is from negative pi over 2 to pi over 2. But again, we'll never reach either one of those because they're asymptotes, so we have to use rounded brackets. That's really all I've got about arctan. Yeah, let's look at a couple problems, guys. All right, so let's look at these 3 different examples. To start off with, we've got arc cosine of the square root of 2 over 2. Well, what this is asking us for is to find the angle such that cosine is equal to the square root of 2 over 2. Well, cosine of pi over 4 is equal to the square root of 2 over 2, and so is cosine of negative pi over 4. But here's the thing, only one of those is in the domain, in the range of our cosine. One of these two has to be between 0 and pi. But we know that this negative pi over 4, it's not between 0 and pi. So it has to be the case that the arc cosine of the square root of 2 over 2 is equal to pi over 4. All right, so really quickly some notation. All I'm saying here is because negative pi over 4 is not in, that's what this funny looking E with a line through it means, is not in the interval from 0 to pi. So all we're really saying is we have two possible choices. One of those choices, negative pi over 4, doesn't fit our circumstance, right? It doesn't fall in our range of arc cosine, so we can eliminate it entirely. And because we can eliminate it, we have only one other choice left, and that's pi over 4. So because we have pi over 4 inside of our range, it must be our answer. Okay, what about tangent inverse of negative 1? Well, tangent is equal to negative 1 only at one spot. It's negative pi over 4, right? And because negative pi over 4 is inside that interval of negative pi over 2 to pi over 2, it must be the answer to the inverse tangent of negative 1. Or the arc tangent, you can call it. So, because negative pi over 4 is inside that interval, negative pi over 2 to pi over 2, and because the tangent, negative pi over 4, is equal to negative 1, it must be that the arc tangent of negative 1 is equal to negative pi over 4. All right, so what about this last problem? Arc sine of negative 12. Well, that's not even in our domain, is it? Negative 12 is not between negative 1 and 1. So that doesn't even make sense. It doesn't have an answer. So, does not exist. The end. We're done. Let's look at a couple more problems. All right, so for this next example, want to find the tangent of the arc cosine of 2 over 3. How the hell are we going to do that? Well, we can start by saying, let's bring this up a little bit. First thing we want to do is find out what the arc cosine of 2 over 3 is. I don't know. I don't have that memorized. I have no wild idea what that is. But I do know that cosine of theta is equal to 2 over 3. And I do know that cosine is equal to the adjacent divided by the hypotenuse. So we can draw this out a little bit and get an idea of what's happening here. Maybe if we do that, we can solve this problem. Okay, so we'll draw this out. What we've got is some triangle with an angle of theta. And the cosine of theta is going to be the adjacent over the hypotenuse. So this bottom side is the adjacent side, right? ABJ. So it has a length of 2. The hypotenuse is the side opposite of our right angle, so it's over here. HYP. It has a length of 3. And I have no idea what the length of our opposite edge is. But I know how to find it. The length of the opposite edge squared plus the adjacent edge squared is equal to the length of the hypotenuse squared. So I know 2 of these values. I know the adjacent and the hypotenuse. I know the length of them both. So because of that, we can plug those in. We've got the quantity 2 squared, the quantity 3 squared, and our unknown squared. Well, I can write this out a little bit more. We've got the opposite squared plus 4 is equal to 9. I can subtract 4 from both sides. And we get the opposite squared is equal to 5. because we subtracted 4 from both sides. Well, if that's the case, then taking the square root of both sides, we're going to find out that the opposite is the square root of 5. All right, we just calculated that, so let's write it down. Square root of 5. So at this point, does it even matter then if we find what this angle is? Because we have everything we need to calculate the tangent at that angle, right? We know the opposite, we know the adjacent. So now we can just throw those in. We don't even have to find out what arc cosine of 2 over 3 is, because the geometry gave us everything else. So what I'm saying is, we can say, all right, 86, all of that, we're done with this stuff. Because the tangent of our angle is equal to opposite over adjacent. Because of that, and because we were able to find out what our adjacent and our opposite edges were, the length of them, we can just throw those in now. Well, the opposite is the square root of 5, and the adjacent had a length of 2. So this whole messy, ugly, terrifying looking thing is actually just the square root of 5 over 2. And the way we found it was by working through what we knew. We knew that we wanted to find out what arc cosine of 3 over 2 was. And we knew that that implied the cosine of our angle was equal to 2 over 3. And we know that cosine of an angle is equal to the adjacent, the length of the adjacent leg, divided by the length of the hypotenuse. So that told us that our adjacent leg had a length of 2, our hypotenuse had a length of 3. So we were able to draw that onto a triangle. And we said, well, I know the relationship between the length of all of these. It's Pythagorean theorem. So I'm able to find this opposite length, and I know that whatever my angle was, the tangent of that angle is going to be equal to the fraction, our opposite length divided by our adjacent length. And because I just found those values, I can fill them in. And that's what we did. So sometimes solving these problems won't be as straightforward as saying, let's go to the unit circle. Sometimes we're going to have to dig into the tools that we have a little bit more. We're going to have to look at the machinery, kind of lift up the hood, look at what's in the engine, right? We want to see what's happening underneath the hood. And that's all we did here. We used what we know and worked forward. Having said that, do not expect yourself to be able to look at these problems right away. Like, oh, I know what to do. It's not going to happen right off. You're going to generally be able to follow this method when you have something like the tangent of the arc cosine, generally, but it may not be obvious to you right away. And that's okay. Don't expect it to. This stuff takes time. It is ugly. I know that. So please do not beat yourself up if you look at this and you're like, I don't know how to solve it. Shoot me an email. get up and walk away from the problem for a little while and then come back to it. Give yourself 30-minute breaks. This stuff is going to take a little bit of time for you to get used to. Having said all that, let's look at another example. So for our last example, let's look at solving the sine of the arc cosine of 3 times x, where x is bounded between 0 and 1 over 3. How are we going to solve this? We're going to solve it just like we solved the last problem. We're going to start by saying, okay, because arc cosine of 3 times x is equal to an angle. We know this. What this tells us is that cosine of that angle is equal to 3 times x. And we know that 3 times x is going to be between 1 and -1. Well, just like with that last problem, we know that cosine is equal to our adjacent leg, the length of our adjacent leg, divided by the length of our hypotenuse. Well, this is just going to be 3 times x divided by 1. So we can draw this out as a triangle. So now we just need to find out what this opposite leg is, right? I'm going to call it OP, like we've been calling it. But we know OP squared plus the quantity 3 times x squared is equal to 1 squared. Well, conveniently, we can go ahead and start reducing some of these, right? We don't know what OP is, so we're just going to leave it as OP squared. But we do know that 3x, the quantity squared, is going to be 9x squared. And we know 1 squared is equal to 1. So now we can subtract 9x from both sides, or 9x squared, I mean. This tells us that OP squared is equal to 1 minus the quantity 9 times x squared. I should say the quantity 3x squared or 9 times x. Yeah, doesn't matter. Semantics. From here, we apply the square root. OP is equal to the square root of 1 minus 9x squared. So we just found the length of the opposite edge. It is the square root of 1 minus 9x squared. Okay. Now, we need to go back and look at what we're trying to find. We're trying to find the sine of the arc cosine of 3 times x. And we know the arc cosine of 3 times x is equal to our angle. We also know that sine of our angle is equal to the opposite length divided by the hypotenuse. Well, we just solved for the length of the opposite, and we already found the length of the hypotenuse. So we can go ahead and plug those in. The length of the opposite was the square root of 1, the square root of the quantity 1 minus 9x squared, and the length of the hypotenuse is 1. Well, that reduces down, doesn't it? To just the radical. So all of this is really just equal to the square root of the quantity 1 minus 9x squared. All of this is to say the sine of arc cosine of 3 of x, or 3 times x I should say, is equal to the square root of the quantity 1 minus 9x squared. But, of course, there's one last thing we need to worry about. We need to worry about this. If you notice, all this is saying is that you're not allowed to put in any x values that would make this, everything underneath the radical, negative. Because then we would get an imaginary answer. So we have to tack that on to the end here. Say x is between 0 and 1 over 3. And that's it. That's all we got. Yeah. Having said that, I will let y'all go. If you have any other questions, please feel free to shoot me an email.